Right. So Chandru is the founder of Mafai and brings over 17 years of experience in designing, managing, and scaling database-driven systems. His expertise spans open source databases, high availability architectures, and large-scale deployments across MySQL, ProSQL, MSSQL, NoSQL technologies. Through Mafai, Chandru has helped organizations build resilient, high-performance backend architectures that support heavy concurrency and business continuity. We are pleased to have him with us today as he presents cross-database streaming on AWS, keeping RDS, MySQL, and TIDB in sync with Xstreami. With a loud round of applause, Chandru and his team. Yeah.
Hi. Good evening, everybody. I think everybody had your tea, and I did not wake you guys. So I'm not a very long speaker. I don't want to stretch beyond time and keep you guys waiting. So we'll just jump in. I'm just going to share a simple use case where we had to stream data from one RDS platform into another TIDB database. So how many of you are aware of TIDB? Okay, so TIDB is a very recent flavor of database which is coming up in the market, where it can do OLAP and OLTP together in the same database. So it's very much compressed. It could store compressed data and it could give you a huge throughput of TPS per second. So this is about me. We started Mafai 17 years back. I started my career I have around 25 years of experience, predominantly a database guy. I started Mafai. After that, Miru Technologies, followed by Miru Sports. So 3 entities. And part-time, I do play cricket as well. So this was an interesting use case for one of our logistics client, where we had to move the data from one platform to other, like I said earlier. But the challenge here is not that straightforward. Why somebody had to touch the nose behind just for a simple use case. They wanted their complete dashboard to be available in 0.01 seconds or even much faster than that. That was the expectation from the client. Their complete tracking dashboard, a courier logistics company with more than 400 branches. You could imagine how complex it is with so much courier data moving around the globe. And their complete dashboard to be automated and response should be very, very high. That was the use case given to us, and that's when Xstream came into place, and we thought of an interesting idea and we proposed a solution, and we started working on that product itself from that point in time only, and probably we made it a success. So we will walk you through how we set this up and what was the process behind it, what are the challenges. We'll see. This is how their initial architecture was. They had a database master with multiple slaves, some of them serving different purpose. So they had some reporting system, some tracking system, some transactional operations and things like that were happening. So the part of the problem statement that we're talking about is such a big join across massive number of tables. You could see 17 tables with 128 joins, and 77 unions happened running on a single query. You could imagine the amount of pages this query would have run up to, right? It's a pretty big query. We had at least 1 week time to understand what the query itself was. So such a big query. And on top of that, we had to bring it down to huge concurrency to be solved for the particular use case. So this was the initial benchmark that we had on that particular query. You could see, even with 500 to 700 transactions per second, this query was almost choking up the 100% of the CPU. And the response time was almost stalled. The server was almost going to hung state. So what we thought was, we'll bring in a solution which will solve this complete summary of tracking, summary movement history, summary package detail, and summary customer details. This is how we want the application to pull out from a simple subset. Predominantly we are thinking of a solution which will denormalize the complete output into a single table, so that, or few tables, from 17 tables to few tables, and run a single query against a primary key. So that was the thing we had in mind. So we had a RDS system from where we were actually pulling the data, and it has to go into an end system of a TIDB. So why we chose TIDB was because it can do OLAP and OLTP, and it was very high transactional processing system. Almost like, if you have to even read if your MySQL can do it in 16 minutes, TIDB can do it in 0.01 seconds. That was the kind of response time we were initially getting from TIDB also. So That was also adding to the Xstream's advantage, and that is where we took up a streamer project. So YTB I already. So what we did is we pulled the data even before it goes into the other databases like slaves and things like that. We started reading the data from the binary logs. So that's what it is, CDCs, change data capture. So any changes to the data that gets returned into this particular log, we read from there. Any transaction that gets returned into this log was recorded. Without even making it persistent, in the memory, we started computing this data. We were able to identify which module this data has to go into. For example, somebody does a booking. So we would understand where this booking reflects in the dashboard. So we identified 5 tables which it has to go to. Let's assume we identified it as 5 tables. So we pulled the record, pushed it into another 5 tables by keeping it in memory, and we were able to process it. We did multiple streamers running in parallel, looking out for non-conflicting roles inside the same database or same events. We call them as events coming into the binary log. So we started processing them. There were a lot of bottlenecks, implementing parallelism and achieving such high concurrency. So this was the complete what we did advantages. We had a very good initiative UI where we could drag and drop the columns. We will tell this is the source column A, and it has to go into the destination in this particular table. It had a very beautiful UI. It was stateless. We never wanted to make the data persistent to make it much faster. We had implemented parallelism. It could do cross-database platform replication. From MySQL to TiDB, it can go from Postgres to TiDB, or it can go from MySQL to Postgres. Xstream could do all these cross-platform replication capabilities. It can also act as a feed for any of the AML. So generally, when this particular architecture happens, people find it very difficult whenever there is a schema change happening on the source that you're trying to do. So we had set up another engine that will actually detect any alters or any schema changes that happens in the primary source of your data. And that ensures, the data schema integrity across the destinations. So this is a typical stack that we have implemented as of now. So it can go from Postgres, Mongo, TiDB, MySQL to same N cross M matrix. So this was the final solution that actually we implemented. So from the master, it went into the slaves, and we had a Xstream which was taking the feed from one of the slaves, and it was pushing into the TiDB. TiDB was serving both the tracking application as well as the AI. So initially, it was very complex for us to maintain the parent-child relationship which was existing in the current vendor, because they had so much complexity across 16 tables, 17 tables. They had constraints which were implemented. So it was very complex for us to really crack that particular logic. And the expectation of high throughput was again hindering us. Schemas were continuously changing. We implemented a dynamic rule update. So which means anybody makes a change, we were able to on the fly pick up this rule as a change. And we were able to implement that particular rule to implement the data across all the destination. Today you tell a record on a column table or a table X should go into a C table or D table. Tomorrow you are changing it. Somewhere you make some changes across some columns. Then streamer can pick it up automatically and it can make the changes across destination. Let's assume you have a JSON object which is there in your source. Our streamer can actually go into the JSON objects, nested JSON objects, and it could tell the complex logics inside a JSON, and again, you can rewrite logics there also. Bulk write requirements, we had almost like millions of transactions per second, and it has to handle that many insert throughput. So after Xstream was implemented, this was the benchmark that we were able to do. Instead of 500 to 700 transactions per second, we were able to very easily scale up to 2,000 transactions per second. And with a very simple use case, we were able to do 1 lakh TPS. In 1 second, we were able to achieve for the particular complete dashboard. The dashboard was loading for 1 lakh clients in 1 second. It also brought down your CPU usage from 95%. Initial usage was 95. We brought it down to less than 20%, and the slow query throughput, almost they had 6,800 slow queries, I think 6,300 slow queries. It came down to 0 to 1. So such a massive improvement we were able to bring in by bringing in this Xstream component into this place. So that's what we achieved by bringing in Xstreami. So Xstream actually can not only serve the purpose of implementing analytics output, but actually you could think of your own use case. For example, if there is a lower version of MySQL or Postgres, MySQL always tells you can't go behind the lower version. So you could write your own rules and tell you do a migration. As a fallback plan, you can bring in Xstream, and you could tell write your own rules, and it could go back to the old version also. So interesting use cases. You could define your own use case and think of ways of implementing Xstream in your own, say, battlefields. Thank you.